For the purposes of understanding nutrient cycling in ecosystems, it's important to not only understand patterns of nutrient uptake, but also nutrient use by plants. Nitrogen and phosphorus co-limit plant growth in most terrestrial ecosystems in the short term, just as in aquatic ecosystems. So, if we take a look at figure 8.3 again, this time we're going to take a look at it for terrestrial ecosystems. And if you remember, on the y-axis we have the natural log, or the response ratio, where no response is 0. And anything positive means that adding nitrogen, phosphorus, or nitrogen and phosphorus together leads to an increase in production. So, grasslands, forests, shrublands, tundra, wetland, all of these bars are above 0, which means that in a grassland, if you add nitrogen, phosphorus, or the two together, you see an increase in growth. If you look in forests, nitrogen, phosphorus, and NP together, all of those increase growth. These are short-term assays. They might take a couple years, for example, but still they're considered short-term assessments of the limitation of productivity to nitrogen and phosphorus. And in general, because these organisms live a long time, so individual grasses within ecosystems can last 20, 30 years. Forest trees can go hundreds of years, for example. It takes time to understand the long-term ramifications of increasing nutrient availability. That being said, short-term, we see a response to both nitrogen and phosphorus across a wide range of terrestrial ecosystems. Now, the authors give you the impression also that N to P ratios in plants are predictive. So those ecosystems that tend to be more limited by nitrogen, so if they're nitrogen limited, that's going to be correlated with having a low N to P ratio. And phosphorus limitation tends to be correlated with having a high N to P ratio, with the idea that if nitrogen is not provided in excess, it's a limiting factor, it tends to have lower concentrations relative to phosphorus than you would expect under optimal conditions. And when nitrogen is supplied in excess relative to phosphorus, you get a high N to P ratio. So on a broad scale, this holds to a certain degree. But in general, it's only sometimes that you can actually use the actual N to P ratio of a plant to predict whether it's limited by nitrogen or phosphorus. When people have done studies to take a look at nutrient concentrations and how well it predicts patterns of limitation, it's essentially only worked once. I'm just going to star this because this is slightly different than what the book is going to tell you. And it's a little bit extreme to say it's only worked once, but essentially this is the one study where it really worked well. So they looked here at the relationship between nitrogen and phosphorus concentrations of leaves in heath plants in Europe. And this was at a relatively wet site. So think of it more like a wetland or a wet grassland. But each data point represents a site where they looked at the N concentrations and the P concentrations of leaves, and then did additions of nitrogen, phosphorus, or both of them, and looked at the response. And what they found was that the ratio of N to P can be generated by looking at the N and P concentrations. Here, N to P is shown in molar ratios, so the ratio of the molar concentration of N and P. But essentially, there's a relatively narrow window where you had co-limitation by N to P, and this was considered to be an optimal ratio. And then whenever you had P in excess, so you're above this line, you had N limitation. And when nitrogen was in excess within the plant, you had P limitation. So it worked really well in this one study, but subsequent studies have found that N to P ratios are a relatively poor predictor of relative limitation of nitrogen and phosphorus. When we look in general at the patterns of limitation, we often see that short-term co-limitation is pervasive. But why is co-limitation so pervasive? Why in general, when we add nitrogen or phosphorus, do we see a response? But when we add N and P together, do we see an even greater response? Well, there's a number of reasons that co-limitation can be generated in ecosystems. For example, plants adjust physiologically to minimize limitation by any single nutrient. So if there's differential allocation, for example, to nitrogen uptake as phosphorus uptake, we know that plants can increase their capacity to take in the more limiting of the nutrient. In addition, if N and P, for example, are taken up in different parts of the soil, plants respond to differences in availability by proliferating where the relative availability of the most limiting nutrient is high. So there's different ways that plants can adjust to balance the opportunities to acquire different limiting resources. Plants also can increase the availability of the most limiting nutrient. So if you take a look at the supply of N to P, so N supply and P supply, and if it's skewed such that there's a lot more nitrogen being supplied than phosphorus, then plants can do things to increase the phosphorus supply. And we talked about some of those mechanisms. So whichever nutrient is most limiting, the plant can increase the availability of that nutrient so that the ratio of supplies is more similar to the ratio to which plants desire those nutrients being supplied. That being said, there are limitations to co-limitation. There's only so much that plants can do to increase the availability or the ability to take up the most limiting resource. For example, when the ultimate limitation of a resource is the abundance of rocks that generate that nutrient. So for example, phosphorus is a rock-derived nutrient, and there's only so much phosphorus that's going to be present in the rocks below an ecosystem. Plants can do very little to increase the availability of something like phosphorus when there just isn't much of it around. And so it runs into a wall as far as being able to increase the availability of that nutrient. So that's what generates ultimate or distal limitation, and why we don't have everything being co-limited by all resources.